Engineering 305, this is Chapter 5, Section 8. This is the first section on pressure vessels. This relates to the thin wall pressure vessels. The next section will be about thick wall pressure vessels. I tell you that because our course learning objective is to be able to evaluate stresses as thin and thick wall pressure vessels, and this learning objectives applies both to this topic and to the next. The equations from the study guide related to this section are the thin wall pressure vessel equation for a sphere, the thin wall pressure vessel equation for a cylinder along its axial direction, along its axis, and then also the cylinder for the hoop stresses, which are perpendicular to the axial direction. I guess that's the best way to say it. We'll explore those more as we go through this this section. So what is a thin wall pressure vessels? Well, really this is the assumption that there is no bending in play and that the radial stresses don't really matter at this point. So the next topic, as I said, is thick wall pressure vessels, and we'll worry more about the difference then, and we'll actually be able to evaluate it. I'm not sure if I assign that as a homework problem this year. Sometimes I do that as a test problem, just to warn you. So I'll give you some examples of thin wall pressure vessels. The first example is a soda can. That is actually my third favorite example. It might be my fourth if I thought about it for a little bit longer, but it's my as far as this presentation goes, it's my third favorite. My second favorite is the propane tank that goes to your barbecue grill. Not only does it go to a barbecue grill at our house, it also goes to a flamethrower, and it goes to a little patio heater so that my wife and I can sit out on the deck a little bit longer in the evening, in the fall, and enjoy the outdoors a little tiny bit longer. But my favorite, of course, is the scuba tank. Now, these are examples of scuba tanks that have ruptured. And I want you to see these pictures and kind of take notes. We will revisit these at the end of the lecture. This chapter is a little different in that we are actually going to derive the equations, and the reason we're doing that is I think the process of deriving them is fairly straightforward, and I think there's benefit when it's this easy. There's definitely benefit to seeing exactly where the equation comes from. So we're going to start with, in a sense, a free body diagram. We'll start by looking at, okay, imagine it's round. And I don't mean just a circle, but I mean imagine that that's a sphere. And now we're going to cut it along that plane like that. And so what you're going to see is it's going to look right like that. And if I look at it, if I look at it from that direction, it's going to look like that. And this is, by definition, thin. By definition, that is thin. Now, I can say that it's got some thickness to it, but it's thin. Now, if I split that, I'm going to have forces working on this thing. So if I had a pressure on the inside, P acting here, then on this, I'm going to have pressure acting all on that face that got cut, or if it's not acting there, it'll be acting all the way in if you consider that. And then I'm going to have a resisting force to hold this thing together. That's the way my internal pressure is acting. I'm going to have a force acting out that's pulling it back, keeping it connected to the other side. And so I've got some force here, and I've got that same force there, and I've got some pressure acting in. Now, if I want to know the stress, that's in the material right there, that stress is equal to the force divided by the area. Well, what's the force? Well, the force is the pressure acting to keep that all. I've got a free body diagram in a sense. I know that force F, I know that force F is equal to the pressure times the area. And this right here, that's my area. So that's equal to pressure times area, which is pi times the radius squared. And I'll label this that's my radius squared. Now, what's this area here? This is the area of the material, this area here. What's that area? That's the area of the material that's supporting that load, which is just this thin blue line all the way around there. So what's the area of that thin blue line? Well, if I cut that again, if I took that, cut it, and rolled it out around this, then this would be 2 pi r, just the circumference, and then this is the thickness. So this is now 2 pi r times the thickness. And you can see stuff is going to cancel out. I'm going to get stuck with a p on the top. I'm going to cancel a pi, and I'm going to cancel an r. And that's going to leave me with a pr over 2t. And that is my equation. That is my equation for stress in a sphere from an internal pressure. All right, PR over 2T. And it doesn't matter whether I cut it on the vertical line that I had shown or if I would cut it on this line. As long as I'm cutting it so that I'm getting half of it, my equation is going to line up. Whatever I derive is going to line up the same way. And if I cut it across a section like this, it's just going to add a lot of sines and cosines in geometry, but it's going to be the same. It's going to be the same. So that's a good simple derivation. I'm glad we did that. Let's keep going. Let's look at a cylinder or the cylindrical equations. And in order to do that, we're going to draw my cylinder. And really what a cylinder is, a cylindrical pressure vessel is, let's try it again. There's my cylinder, and I'm going to cap that at the top and bottom with a sphere. So that's a sphere, and that's a sphere, and this is a cylinder. Now, I think if you start to think about this, what you're going to see is if I split that along a horizontal line, depending on where I put it, I'm going to have a pressure here acting down. And if I look, it's going to look exactly the same as what we just did. I'm going to have, if I look in, get my colors right. If I'm looking that direction, what that's going to look like is I'm going to have a red circle and I'm going to have a pressure acting inward, and the pressure, the force from that is going to be equal to the pressure times the area, which is equal to the pressure times pi r squared. And then this little line here, that's my area. That's still going to be stress is equal to P times pi r squared. That area is still going to be 2 pi r times the thickness. And I'm going to get the same equation. And that's true. That's true no matter where I shift this cut, no matter where I take that cut. I think you could see if I eliminated the cylindrical section and just put the two halves together, I'd be back to a sphere. This horizontal cut really doesn't tell us anything interesting at all, but I use it to get back to the same place where we were. An equation that my axial stress in a pressure vessel, in a thin wall pressure vessel, is equal to PR over 2T. Let's keep going. Let's take that same pressure vessel, and I'm going to draw my two walls, and then I'm going to draw my ends. And I didn't do it well, but you should know that. It's the best I can do. Sphere, sphere, and then I've got my cylinder in the middle. Now, this time I'm going to split it this way. And the problem is going to become, it depends, my stresses are going to depend on how long my cylinder is compared to my ends. So what I'm going to do is I'm going to say that this dimension here is infinite. That dimension there is infinite. And I know you're going to go, Now what I get when I split this is just get that. And I have my pressure. I have my pressure acting on this whole face, which is it's rounded, right? But it's going to be acting inward. It's going to be acting on that whole face. And then I just have this little edge here. That little edge to support the stress. If I look at it from the top, it looks like this. And I have my pressure acting inward. And I have this edge and I have this edge supporting the load. Now, what's my force? If I do this is, and to go back to my other, I'm going to have my reaction force this way. So my stress is equal to a force over an area. This force has to be equal to the pressure times an area. And what's that? What's the area of this? Well, pressure. The area is the diameter, or I'm going to call it 2 times the radius. And the reason I'm doing that is because I want to compare this equation to the previous equation. It's 2 times the radius times that length or that height of that zone. I called it infinity, so let's put it down as infinity, even though that's going to be hard to do the math on, but that's okay. And then what's the area, what's this area that's now resisting? What's this area of this? Well, that's going to be this length or this height. Okay, well that works out because that's infinity. And it's going to be times the thickness of the material, but I've got 2 of them. That would be infinity times times the thickness would be the size of 1. So I've got to put that there. And now it starts to look familiar, but it's a little bit different. I'm going to cross out my 2 and I'm going to cross out my infinities. And now I've got my stress is equal to PR over T. And this is for a stress that is going in and out of the page, right? It's going in and out of the page here and here. It's actually going in this direction. The other stress that we did was in the axial direction. When we split it horizontally, we were looking at this force. When we split it vertically, we're looking at that force. So we've got 2 equations now. And so now let's start comparing them. I have my cylinder. Actually, you know what? And I split it this way. And that gave me my spherical stress equal to PR over 2T. And then I split this vertically, and I got my axial stress, because that's along the axis of the cylinder, that was equal to PR over 2T. And in some ways you can see that if I had taken and put that split at that line, then it would have had half a hemisphere, or I would have had a hemisphere. It would have been half a sphere. So I get the same thing. If however, I'm really struggling with the drawing here. If, however, I take this and I split it this way to get this stress across here, that is sigma H, and you could say that's for horizontal, but it's not, because I could turn that cylinder. It's called hoop. That is PR over T. Now, which is the largest? Well, that's clear. That's clear. The hoop stress is equal to twice the axial stress. And the reason it's called a hoop is because the way I'm going to solve this problem is I'm going to put hoops around this to help hold that stress in. Is that interesting to us? Maybe, maybe not. Take a look at this. Remember the picture? How did these things break? They broke on a line like that. Why? Because my stress was the highest that way. That's my highest stress. It's twice the stress in the other direction, so it's not surprising. That's the way that I'm seeing my failures. It's exactly the same way you're going to see a LaCroix can that I left in the freezer. It's exactly the same way that can split. It's the reason that whiskey barrels or wine barrels or barrels in general have steel straps around in the equatorial direction. We have barrel hoops in order to help contain that stress. That's the reason the construction of a barrel is the way that it is. Those straps help hold and contain all of that stress. All right, the next presentation, the next video I'm going to do will be example problem 5-16. We're going to look at the stresses on a cylindrical pressure vessel, and we'll start seeing how some of these equations get used and what we learn about it. All right, hope you're doing well. There'll be more to come.